Hello class, this is Tim Tomlanovich. Welcome to Structural Analysis 1. I'm going to go over this PowerPoint and get you started with Learning Plan 1. So our course competency 1 is relate concepts of mass and acceleration to force. Okay, so our objective today is we're going to recognize the relationship between force, mass, and acceleration. We're going to identify units of force, mass, and acceleration using US and metric units of measurements. And we're going to describe forces using magnitude, direction, sense, and point of application. Okay, so fill in the answers on your handout. Okay, so let me go to Blackboard here. If you go into Blackboard, and there's this lecture sheet attached underneath the PowerPoint. So I'm in Learning Plan 1. Okay, here is the PowerPoint I'm going through right now. If you open this lecture sheet, which is this guy, this is another way for you just to write down the important things that I want you to know. Okay, so it's not homework. I'm not going to collect it, but it's for you to help summarize basically what I'm talking about in this PowerPoint. Okay, so with that, that's what this is all about here. Okay, so force equals mass times acceleration. So what is a force? It is a vector. Force is a vector. So if you look here, we have wind loads, we have dead loads, live loads, weights of materials. That's what a force is. So if you look at our main force is gravity, the weight of materials pushing down on the earth, okay? And then we have dynamic loads such as earthquake loads. We have wind loads, which is a dynamic load. We have snow loads, which is a static load. Okay, we have roof loads, weight of materials. Those are static loads. Okay, so basically what we're doing is we're talking about this force. We're taking the weights of materials and turning it into a force vector so we can figure out how strong to make these. And this is where we'll end up way at the last structural analysis too. Okay, so let's look at the units of force. Metric system, it's a unit, which is kilograms times meter per second squared. And the US system is pounds. Okay, you can also see kips. Okay, we got kips or tons. Okay, so for a force system, mass is the amount of matter in an object. Okay, metric system is 1 kilogram. US is 1 slug. Okay, so and then we have acceleration is the velocity rate of change. Okay, that's 9.81 meters per second squared or 32.2 feet per second squared. Okay, that is gravity. Okay, what is acceleration? So when you set the cruise control to 55 miles an hour, okay, and then all of a sudden you hit the gas pedal and you change it to 60, that is acceleration. Okay, and then the mass of your car is times the mass of your car will equal the force of that car. Now, what's the difference between force and mass? Now remember, let me back up. So mass is basically how much it weighs. So when you weigh yourself on the scale, that is actually a force. That is not a mass because that does not include gravity. So mass does not include gravity. So that is like when we're in outer space, no gravity. Okay, so force equals mass times acceleration. Okay, and then your force, this is what we're going to be dealing with basically the 2 semesters with me, forces. So we have dead loads, we have live loads, okay, and typically your dead loads are your weights of materials, live loads are people, wind loads, okay, snow loads, rain loads, etc. So that's why I'm introducing you to this. So weight is the same as force, okay? Weight is mass times gravity. So if you notice here, okay, if you notice, what do we have here? Gravity is 9.81 meters per second squared, US is 32.2 feet per second squared. Again, what I'm saying is that when you weigh yourself in a scale or you're weighing materials in a lab, it's a force or a weight. It's not mass. So sometimes we interchange that term mass. What is the mass of that object? Okay. So that mass of that object is actually weight or force because it includes gravity. Okay. Let's go take a look at, let's see here. Let's see if I can double click on that. Let's see. Let's open link. Let's take a look at this. It's kind of a neat little thing. So this PowerPoint is attached in Blackboard. Okay. And you will be able to review this as many times as you want. I thought these are really nice here. Okay, mass versus weight. Mass and weight are different quantities. Mass is the amount of matter an object contains. The size of the object does not determine its mass. Big plastic foam block does not contain as much mass as a small lead block. Okay, remember masses consist of atoms. Bowling ball and a soccer ball are about the same size, but the bowling ball has more mass. It contains more matter. Okay. The mass of an object remains constant. It does not depend on its surroundings. So no matter where we are on the Earth or the Moon, mass does not change. It's gravity what changes. The weight of an object can change with location. Okay, if the force of gravity increases, the weight of the object increases. If the force of gravity decreases, the weight of the object decreases. So it's about 1/6 of, gravity is about 1/6 of what it is on Earth. Jupiter is 2.53 times that of gravity on Earth. Okay, so I weigh 2.53 times more on Jupiter than I do on Earth. Basically, that's what that's saying, because my mass is the same. Okay. Oops. Let's go back. All right. Now I just got to figure out how to get out of here. Okay. So back to the PowerPoint. All right, so weight equals force, and force are our weights of our objects, that's what is in our building. Okay, now let's talk about the characteristics of a force. Okay, we have a magnitude, that's the quantity of the force. So the magnitude is the F, the force equals mass times acceleration, okay, is that value. It's pounds, kips, tons, newtons, kilonewtons, okay. The point of application is the point where the force is applied, okay? All right, so if I look right here, here is my point of application. It's like pretend there's a cable attached to this little bracket here. So it's actually pulling, this cable is actually pulling right there. That's my point of application, okay? If I look at this force vector, these little arrows are force vectors. My point of application, believe it or not, is sitting right there, okay? So if I look at what's happening here, here's the snow load, here's the roof dead load. What we do is we turn these force vectors, okay, and we determine the point of application. So the top of the wall, the roof loads and the snow load is actually held right there at the top of the wall. Okay, and then the weights of all these materials is held right here. Then we got the floor joists coming over. Points of application. Okay, points of application is where the force is being applied to. So right here on the bottom here is the bottom of the footing. Okay, the sense is the way the force acts along the line of action. All right, let's go to the line of action. Path of the line of action, the path, the line along which the force acts. Okay, so here is my line of action. So if I look at this right here, my line of action can extend infinitely in the same direction, from same angle from x-axis, infinitely in both directions. Okay, so no matter how I look at it, okay, so if I look at right here, see what I'm doing is I can move this force vector along this line of action as long as the magnitude stays the same, and as long as my line of action stays the same and my senses stay the same. This bracket is moving this way. Would you agree? So let's take a look at the line of action of the walls. So if you look at the roof load, okay, each of these line of actions are basically the shaft of the arrow. Okay, so here's the line of actions of all these wall loads are right here. Okay, so we can convert that, and this will be later. See, my line of action is vertical. Okay, so basically this roof load is it's called principal transmissibility. We can take this roof load and transfer it all the way down to the footing, because the footing is actually holding up the roof load. It just because the line of action is the same. Okay, now sense is the arrowhead. If we look at the sense here, arrowheads, it's usually a north, south, east, west direction. So north, south, east, west. Okay, so this one I would say is northeast. This is a northeast sense. This is a southern south sense. This sense is acting north because it's pointing up, so it's the direction of the arrow. Okay, so we have four characteristics: magnitude, point of application, where it's acting, sense, which way the force is acting, and the line of action. So these, you need all four of these for us to do structural analysis on a building. Okay, so let's move on. All right, let's talk about Newton's law. Newton's first law. Any object at rest will stay at rest, and any moving object will continue to move at the speed in the same straight line unless a net force acts on it. Okay, so I'm going to, let's look at Newton's first law. And why is this important? This will, I don't know if you can hear this. So if you can't hear this video right now, you can go right into the PowerPoint in Blackboard and you can listen to it. Okay. Let me. All right, the Newton's first law. Any object at rest will stay at rest, and any moving object will continue to move at a speed at the same straight line unless the net force acts on it. Why is that important? Okay. Why is that important? So, if we just go back to this right here, basically the weight of these materials is acting on a force down. Okay, it's putting, and the soil pressure is pushing back up. So the soil pressure has to resist the forces acting down. Okay, so because our buildings are not moving, we got to be in a static location. Okay. All right. Let's listen to Newton's second law. All right. Newton's third law. So for every force of action, there is a reaction that is equal in magnitude, opposite in sense, and has the same line of action. So let's watch that video, and then we'll start doing some examples, and you can see how these are related to structural analysis. Okay, so, all right, so reason why I think this is good, just to review if you had physics already, this explains forces and how these react. We use these laws when we do structural analysis and statics to keep things still, otherwise everything would be moving. Okay, let's do an example. Okay, example 1. If the truck weighs 15 kilograms and a person is pushing the truck at 4 meters per second, how much force is being applied to the truck by the person? Okay. All right. So remember Newton's second law, force equals mass times acceleration. Okay. So this should be meters per second squared. So our force equals 15 kilograms times 4 meters per second squared, and that will equal a Newton. Okay, so 15 times 4 equals 60 newtons. Okay, so basically, if I look at this force vector, okay, my sense is the arrowhead is pointing to the west. My point of application is right there, right where his hands are. My line of action is pretty much horizontal. Okay, right? This is the line of action. Okay. And then my magnitude is 60 newtons. So he's pushing this truck to the west with 60 newtons of force. Okay. So there's the 4 components: sense, line of action, point of application, and magnitude. Okay. So force equals mass times acceleration. All right. Okay, next one. Calculate the mass of a person if they weigh 200 pounds on Earth. Okay, so number 1, we know force equals mass times acceleration, or weight equals mass times gravity. Okay, so we're going to use this guy because we're talking about weight. So the mass, we want to solve for m, right? So weight divided by gravity equals mass. Okay, so our weight is 200 pounds. And our gravity on the moon is, if you look, it's right on, we can go right here. The gravity on the moon is 5.3 feet per second squared. Second squared. And number, it's English units, so that's going to be a slug. 200 divided by 5.3, and I get 37.73 slugs. Equals mass. So that's problem 1. Okay. What would the person weigh if they were on the moon? Okay. All right. Oh, I'm sorry. So this actually is, I misread the question. So let's do an eraser here. Okay. The question is asking, calculate the mass of a person if they weigh 200 pounds on Earth. So I know the gravity on Earth is 32.2 feet per second squared. So 200 divided by 32.2, that's 6.21 slugs. Okay? All right. So we know mass is the same on Earth and on the moon, no matter what, and on Jupiter, whatever. It's just the gravity that creates it into the weight and the force. So weight equals mass. Okay, so this is problem 2. So our mass is 6.21 slugs. And we're going to multiply times our gravity, which is, I do believe it was 5.3. Moon, 5.3 feet per second squared. And then we get times 5. Okay, 6.21 times 5.3. I get 32.9 pounds. 0.9 pounds. So that's how much a 200-pound person weighs on Earth. He weighs 32.9 pounds on the moon. Okay, this is a final answer. Okay, the mass is 6.21 slugs. That doesn't matter if you're on the Earth or the moon. Okay, so that's example 2. This using Newton's second law, force equals mass times acceleration. Because they're directly proportional and inversely proportional to the mass, we can rearrange this equation to solve one or the other. Okay, all right. Example 3, identify the 4 characteristics of each force vector in each of the diagrams. Okay. All right, so let's look right here. So our sense, here's our sense, is the arrowhead. And these are all pointing east. Okay. Our point of applications are right here against the building. So I'll do a different color. Here's my, so obviously we would need to know a certain distance from the ground or from the roof. So these are my point of applications. Okay. And the green. All right. The line of actions. So each one has a different line of action. They're all basically 0 degrees from horizontal, right? The shaft of the arrow. Okay. And then my magnitude is FR, F4, F3, and F2. Each of them have a separate magnitude. Okay. All right. So let's look at this guy. Magnitudes. So B is 600 pounds, A is 400 pounds. Sense for this guy is southwest. Sense for B is southeast. Point of application, they're all right there at point O. Because if you look, the line of application, the line of action, do they intersect at a common point? And if I project the shaft of the arrowhead, they come to a common point. Okay, because due to principle of transmissibility, my force, this is my point of application is at point O, and then my line of action for force vector A is 30 degrees from horizontal and 45 degrees from horizontal for force vector B. Okay. All right. So, all right, force. Okay, point of application for this guy is right here, 8 feet over from this wall. My magnitude, obviously, is a weight of the safe. My line of action is this line projected down, and we have our sense is south. Okay. All right. So there we go. So that's for our 4 characteristics of that force. Different examples of how, so these over here on the right could be wind loads that were creating force vectors. Okay. These could be cables or power lines or guy lines acting from this transmission line, holding this cell phone tower up or transmission line tower up. And here is, we have a force acting on this floor beam, right? So we need to know where that point of application is so we can actually calculate the strength of this beam, how big to make that beam based on that force. Okay. All right. So another example. What is the magnitude of the resultants? All right, so if we look here, we have a 4 Newton pushing down, a 6 Newton pushing down, and a 16 Newton pushing up. Okay, so the resultant, because we can assume that the line of action, the 6 Newton force and the 4 Newton force, we're going to assume that they're on the same line of action. Okay, so we can go, we know this is negative 4 newtons because it's pointing down, minus 6 newtons plus 16 newtons, okay, because this is pointing up. All right, so we got negative 10 plus 6, so we're left with 6 newtons. So if I look at this, okay, welcome back. Sorry, got interrupted there. Okay, so we have 6 newtons, okay, is our magnitude of the resultant, okay? So basically, just like our sense, we have north, south, east, west. We know everything that's pointing up is going to be positive. So I'm looking at the arrowheads, and anything that's pointing down is going to be negative, and then anything pointing to the right is positive. Anything pointing to the left or west is negative. So that's kind of a typical coordinate system we use in structural analysis. Okay. So now my resultant is, so if I draw this box again, we know it's 3 kilograms. Okay. And then we have a resultant of 6 newtons going up, right? So this object is moving up because I have 10 newtons pushing down. I added the ones pushing down, and I added the ones pushing up, and the difference is 6 newtons. So this object is moving to the north. Okay, so that is question number 2. The sense is north. What is the sense of the resultant? And the answer is north. And then what is the acceleration of the object? So that's number 3. So if we go force equals mass times acceleration, force divided by mass equals acceleration. And then we have 6 newtons, okay, divided by acceleration, and that is 9.81 meters per second squared. And then if I do my math, 6 divided by 9.81, I get 0. I'm sorry, that's not acceleration. That's not mass. That's acceleration of gravity, because I have my mass here is 3 kilograms. So 6 divided by 3 is 2. So 2 meters per second squared. Okay, we only use gravity if we're talking about gravity, but because this thing is moving at a force to the north and it has a mass, we can actually back calculate the acceleration. I apologize for that. All right, so what is the magnitude of the resultant? 6 newtons. The sense is north, and the acceleration is 2 meters per second squared. Okay, so with that, so typically if we were face-to-face, so unfortunately we're in a different circumstance, we would do a Kahoot, and we could go through everything to help you remember things. So your homework is read pages 15 and 22 of your textbook and do CC1, stands for Course Competency 1 homework, which you can find in Blackboard. Okay, so again, if I'm in the content, here's the homework. And if you look here, here is your homework. Now I'm not going to collect this. This is for you so you understand what's going on, and then we'll have a quiz. Okay? All right. So with that, I do believe that's it for this Learning Plan 1 lecture. Thank you. And please let me know if you have any questions.